You know, deep beneath our feet, in what looks like totally solid rock, there's a constant invisible battle going on. It's a war between different fluids, all fighting to get through the same tiny microscopic maze. And figuring out the hidden rules of this underground fight, well, that's one of the biggest challenges we face in managing our energy resources. So that brings us to the big question, right? When we find an oil reservoir, why is it that we often leave more than half of the oil down there? It's because a reservoir isn't some giant underground cave filled with oil. Not at all. It's much more like a gigantic, super compressed rock sponge that's soaked with fluids. And getting the oil out isn't as easy as just sticking a straw in it. No way. It's this incredibly complex stance that's all about physics. Okay, so to really get a handle on this, let's try a different way of thinking. Forget the sponge for a second. Instead, picture this porous rock as a massive, intricate highway system built just for fluids. The design of this highway, well, that changes everything about how things can move. Now, every rock has this basic quality called absolute permeability. We usually just call it K. It's basically a measure of the rock's absolute maximum potential to let fluid through. So, in our highway analogy, think of it as the posted speed limit on a perfectly empty road. We're talking ideal conditions, no traffic. It's a fixed number for that specific piece of rock. But let's be real, when is a highway ever actually empty? Almost never. And that brings us to effective permeability. So if absolute permeability is the potential speed limit, effective permeability is the actual speed of traffic during rush hour. It's not fixed at all. It's constantly changing based on what fluids are in there and how much room they're taking up. So when you've got multiple fluids, let's say oil and water, all trying to use the same highway, things start to get messy. You get an underground traffic jam, and we need to figure out the rules of the road for that jam. And that brings us to the main event, relative permeability. It's actually a pretty simple idea, but it's super powerful. All it is a ratio. You take a fluid's actual flow rate, its effective permeability, and you compare it to the rock's maximum possible flow rate, the absolute permeability. What you get is a number between 0 and 1, and it tells you exactly how well that fluid is dealing with all the traffic. Now, not all fluids act the same in this traffic jam. You can kind of split them into two groups. First, you've got the wetting phase, which we'll call the wall hugger. This fluid loves to stick to the rock surfaces. Water in a sandstone is a perfect example. Then you have the non-wetting phase. This is your lane hog. It avoids the walls and just barrels right down the middle of the biggest, fastest lanes. In our rock, that's the oil. And this difference in behavior, it is absolutely critical. This classic X graph here shows these traffic rules perfectly. Along the bottom, that's how much water is in the rock. As you add more water, its ability to flow, that's the KRW line, it goes up. That makes sense, right? More water, easier flow. But look at the oil curve. And here's the wild part. Even a tiny bit of oil, our lane hog, can completely tank the water's ability to flow. Why? Because that oil is clogging up the biggest, most important pathways, the superhighways of the whole system. Okay, so just when you think you've got the rules all figured out, there's a plot twist. Turns out the rules of this underground traffic jam aren't actually set in stone. They depend on what happened before. The history of the flow itself changes the game. The first process is called drainage. This is when our lane-hugging oil comes in and pushes our wall-hugging water out of the way. You can think of this like the original event millions of years ago when oil first moved into a reservoir that was already filled with water. And then there's the reverse process, which is called imbibition. This is when the water starts to push back and displace the oil. And this is incredibly important because it's exactly what engineers try to make happen when they're pumping water into a reservoir to force more oil out. So this really critical effect, the fact that the rules of flow depend on whether you're adding or removing water, it has a name, hysteresis. And for a reservoir engineer who's trying to predict how a field is going to perform, understanding hysteresis isn't just a good idea, it's absolutely essential. And this graph, this just illustrates the point perfectly. Take a look. You've got two completely separate curves for the oil. The top one is for drainage. That's when oil is pushing water out. The bottom one is for imbibition, when water is pushing oil out. So for the exact same amount of water in the rock, the oil can have two totally different flow rates. The path you took to get there, it changes everything. Okay, so we've got these unbelievably complicated rules that change based on the fluid in its history. So how in the world do you take these tiny microscopic principles and apply them to a real-world reservoir that could be miles wide? Well, it all starts with something really small. These little plugs of rock, just a few inches long, that are drilled right out of the actual reservoir. Scientists then take these core samples back to the lab and they run these meticulous experiments, flooding them with different fluids to map out the exact drainage and imbibition curves for that specific piece of rock. Now here's what's really fascinating. These curves you're seeing, they came from 3 different core samples taken from the very same reservoir. And you can see how the traffic rules are different for each one. A reservoir isn't just one big uniform block. Its properties can change a lot from one place to another. And that creates a huge challenge when you're trying to make predictions for the whole field. So, to handle all that variation, engineers have this really clever 3-step process. First, they normalize all the data from the lab. That just means they put it all on the same scale so they can compare apples to apples. Then, they calculate one single average curve from all those samples to represent the typical traffic rules. And finally, they denormalize that average curve, applying it back to the real-world conditions of the whole reservoir. Okay, so that is a ton of work, right? All this normalizing and averaging. So why go through all the trouble? Why does understanding this tiny, complex, underground traffic jam matter so much? Well, because these ideas have billion-dollar consequences. Seriously. Understanding relative permeability is the only way to accurately predict how much oil you're going to get and for how long. It lets engineers figure out the maximum recovery and design these massive, effective projects like water flooding to push more oil out. Getting this right is the difference between an efficient energy project and leaving huge amounts of a valuable resource trapped underground, forever. It's just a reminder, isn't it, that some of the most powerful forces shaping our world are happening on a scale we can't even see, following these incredibly complex rules we're still trying to fully understand. It just makes you wonder, what other invisible forces, hidden deep down below, are going to be the key to shaping our future?